Hello and welcome back. Okay, in the I/O series, I've started off by adding some GPIO pins, and then we've used those to interface a few different things into the CPU. But I think it's time to start looking at some more widely used protocols and how we can use those pins to start adding other off-the-shelf devices into the system. And this is of course moving slowly towards interfacing circuits I'd like to include in the main build with a particular note on storage. So I want to start by looking at the Serial Peripheral Interface, or SPI. So let's go take a look at the specification on Wikipedia, and then we can start looking at a circuit for it. Okay, I often find Wikipedia is a good place to start looking at things like protocols. So systems used to communicate between devices in microcircuits, the two most common things I see are I2C and SPI, which is what we're going to look at today. SPI is the simpler protocol, so I think it's a better first look. So on a device, you have 4 lines, the device to the host and from the host to device, and you have a chip select. Now, one of the complicating factors of this protocol is the way there are different variations of it. Although if you look at this diagram, you've got 2 types of clock signal and 2 alignments between the clock signal and the signal changes on the data lines. And if you look closely, you realize that this one, C-pole, clock polarity, is just the clock signal being inverted. And the CPHA just determines where the changing of the data aligns with the rising or falling edge of the clock signal. So we can actually implement this with fairly simple circuitry. So the 4 different permutations of these have mode numbers associated with them. One last thing I'd like to comment on is the MOSI and MISO acronyms on this documentation refer to main out sub in or main in and sub out, but you will find other sources of documentation that refer to them as master out slave in or master in slave out. Most people seem to be switching over to the new terms, but you will occasionally come across the other form. It's worth knowing that just to make sense of older documentation. Okay, if we're going to do some SPI interfacing, we need an SPI device to experiment with. And I've got one of these DS1391 chips. Now they only come as an SMD chip, so a while ago I soldered one of those onto a conversion board. So there's a link to that short video in the description. But let's take a look at the datasheet and then start looking at the circuit. Okay, so quick look at the datasheet for the device. Now this datasheet covers multiple versions with different protocols and a few different features. Now interestingly enough, this device has versions that support modes 0 and 2 and 1 and 3, and the device I've got supports mode 1 and 3. Now the main thing to look at here is the operation is very simple. We either have a read where we output an address byte and then we read a byte of data in from the device, or we have a write where we output the address followed immediately by the byte of data we want to write. So the pinout is very simple. We've got a reset line that's not very relevant to us. We need to provide a crystal to provide the timing base. We've got a backup input that would allow us to attach a battery, but then we've got chip select, data in, data out, and the clock. But in the context of the more widely used SPI terminology, this is the sub-device, and as CPU and its GPIO board is going to be the main device. And then the next important thing to look at is this table of the addresses. Now you will notice that the write address and read address are separated by the top bit of the 8-bit address. So we could think of that as read or write followed by 7 bits of address, and the range of values isn't actually very high. It's only 4 bits of relevance. So you've got initially a set of 8 registers, 4 dealing with the date and 4 dealing with the time. There's also alarm features and there's additional control variables, which we're probably not all that worried about today. Okay, well, we probably don't want to look at data sheets too much. Let's actually get this chip, stick it into a breadboard and start experimenting. Okay, so I've got the CPU build out. I've got the GPIO circuit here. I've taken out my temporary working circuits and just left the original GPIO circuit. I'm going to use that to interface this RTC chip. I've got the UART connected to it because we're going to use that for communication with my PC. But I've also left the SNES controller interface going because it's worth noting the SNES controller protocol reminds me a lot of the SPI protocol. There are some subtle differences, but in terms of the kind of logic we need to implement, it's not that dissimilar. I'm going to zoom the camera in so we can see this a bit better. Okay, I've orientated this the way we normally would for a DIP chip. So we can do the ground line and the power line. Now, clock is a pretty important line. That needs to be an output, and I'm going to take the most significant bit of our GPIO, just because the bit at the top and the bit at the bottom are the easiest ones to manipulate using shift instructions. Next line is data out. Let's take that to one of our inputs. I'll use the bottom bit. So the data in line, I'm going to take that from the least significant bit. And then we're going to need a chip select, connecting that to bit 6. Now the needed crystal is 32.768 kilohertz. And when I went and bought one of those, it came in this tiny little package, which I assume is actually designed for watches. I think we can get away without connecting the backup lines at the moment. In theory, we've got what we need. We just need to write some code if we're going to bit bang these lines. And I think it would be best to start off making some definitions to make our code a bit easier. So there's date and day. I'm guessing day with only 3 bits is actually day of week. I'm not interested in that, so let's just take that. Right, let's start with the most basic thing we can do. The hundredths entry is 0, so if we're just outputting a 0 on the data outline and then we just clock 8 times, that should be selecting that register. So let's just do that. Now we're probably going to have multiple chip select lines, so I'm going to start off with every bit set. But the clock is always shown as starting low in the diagrams I was looking at. Let's make the data low, and then we're going to start the transmission by dropping select. So we set the clock line and clear the clock line. So what we should be doing here is literally just generating a square wave for 16 cycles. And then we return back to the start. Actually, I'm going to copy in this little piece of code that I've been using to allow any key on the UART from the keyboard will prevent the loop. I think that'll be an interesting first test. Okay, so this is a pretty trivial sized piece of code. So we can see the bottom bit is low, and that was our data out from the host and data into the real-time clock chip. Chip select and the clock line have a kind of mid-brightness to them, which says there's some activity that's too fast for us to interpret. I think we should fire up the scope and take a look at this. Okay, so let's start off by taking a look at that chip select line. So that's on the yellow trace, and let's also take a look at the clock line. Okay, one thing that's immediately apparent is our clock line spends a lot more time low than it does high. Now that's going to be because we've got quite a short number of instructions between setting it high and setting it low, but let's move the purple line and look at data out, because in theory what we're doing here is writing a 0 to the address, which means we're reading from address 0, so we should actually be seeing data coming back. Excellent. So that feels like we're seeing some rapid binary counting. It's a little bit odd at the start, but the data out is a tri-state. So only when it's outputting data will it drive the line. So I'm going to try putting a pull-up resistor in. That feels a bit more sensible. So what we need to do is modify this code so we are outputting any value we want instead of just 0 for that first half, and we're actually reading the data back in on the second half. I think what we want to do is invent a function. We're going to convert it to a hex string and output that to the serial port. But actually we want to do this in the opposite direction. Let's pull all 4 bytes of the time in. We'll stick a new line at the end. Let's write that function. Okay, so this is kind of our resting state. I don't care about the data at this point. Grab copy of the data we're going to be sending. Right, so if we shift left D into the carry flag, we're going to get the 8 bits in sequence that we want. And we want to put that into the bottom bit of A. So I'm going to shift right A. So whatever the last data bit we were sending was is now in the carry flag. But then we replace it with the top bit of D. And then we shift into the bottom bit of A. So this should output each of those bits in sequence, so we will have written the address. And now we need to do the reverse of that. Now that's going to have the bit of data we want. I'm running out of registers here. Let's go for the easy route. If you want to do clock high, then clock low, and we don't need to worry about manipulating that, even though the immediate loads are going to cost us a couple of cycles. Read it in, and let's assemble our data in B. That feels like we've got everything we need. Let's give it a try. No, I've not taken account of something here. Oh, hang on. This is assuming the data comes back in A and I've got it coming back in B. Probably need to save and restore D and C as well because we overwrite those, and B. We'll thank ourselves later for remembering to do that. Okay, that looks quite promising. So this column's definitely ticking up in seconds. So this would be 43 minutes, and I'm at 52 minutes recording, which would be about right for when I actually put power to the RTC chip for the first time. I think that's working. Okay, I think we can take this a step further. Let's give it the date as well. Actually, let's format this slightly better. Okay, so time values are normally separated by a colon. Apart from hundreds would be a point. And let's output the date as well. Right, this is a risky move for me because I'm in the UK and we do it day of the month, and then year. I appreciate other geographies do it differently, but this is what I'm used to. And then I'm going to annoy everyone by saying it would actually make more sense to do it completely in the opposite order to this, because then an alpha sort of dates would put them in date order. I think a forward slash is the most common convention there, and a space. Give that a quick run. That definitely looks more like a date and time, but it is not the 1st of January 00. So we're going to need to be able to write to this to set the time. Right, so let's assume we write a function where we take B as the value. Okay, almost tripped myself up there. So you notice we're outputting hex. That's because this chip is working in binary coded decimal. So I actually need to set 23 in hex as the year. So I need to write this function. Now, when we're writing, we need to set that top bit that determines it's a write address. And just set that there. And then B is the data we're writing. So I'm just going to save that off while we're writing the address. This bit's all the same. So we can just pop that straight into D, and then it's basically just this code again. So we're just doing 2 8-bit writes in a row. Should have done that one first, actually, although we wouldn't have seen the results. Okay, this is actually feeling quite a lot simpler than I thought it was going to be at the start. Let's give that a go. Didn't change, so we've not got it quite right. I'm presuming A is preserved and I'm overwriting it there. Let's do that there. Bingo. Right, let's take the scope out. Should have turned that off a while ago. I do need to experiment with more ways of reducing the sound from that. So at the moment I turn it off, I suddenly realise how loud it's been in the peripheral of my hearing. Let's disconnect this thing, plug it back in, and try running that again. So the time is reset. So I've got one of these CR2032 battery holders and it doesn't want to stay in the breadboard. Had a similar problem with some of the dip switches, so I've stuck some pin headers on the bottom. That should stay in now. I believe ground is the middle pin. So that's on at 2 minutes 40. Power cycle it now, and it's come back at the same time. Excellent, that's working. Now, need to set the date and time fully. I don't want to keep writing code, so let's just see if we can modify this. Change that to month. It is December at the time of recording. Hey! And it is the 4th of December. Now time's going to be a bit more tricky. I really need to write a time set utility once all is said and done, but for now this is kind of fun. Don't care about hundredths, let's set hours. There is a bit to define 12 or 24 hour clock, but I think we're safe to ignore it right now. Right, so it's 11 o'clock. Right, so it's going to be 2 minutes past next. So I'm just going to wait till it's exactly 2 minutes past, then reset seconds to 0. Of course, I've made a mistake there and included that write inside the loop. Okay, so it's off by a few seconds there, but that looks like it's keeping time. And if I've done it right with the backup battery, I should be able to turn it all off and have it keep the time. So I'm going to power that up tomorrow and see if the date and time is held. That's awesome. I think that's a good piece of progress for today. Okay, that was fun. It's quite rewarding to get that working. But what we've been doing is implementing the SPI protocol by modifying the lines on our GPIO directly, what we call bit banging. And I'm not too convinced by the speed of that, particularly if I'm going to use it for larger data transfer to other devices. It's fine for this real-time clock chip. But let's have a look at the program code that we ended up with for the read and think about the time it's going to take to read a larger amount of data. Now, devices that transfer more data usually allow us to do some kind of setup and then repeat this byte reading process in order to read sequential bytes of data in. So for transferring a larger amount of data, we're only really worried about how long this takes. And of course, the looping structure here, if we were trying to optimize this code, we could just take this chunk out and reproduce that 8 times. So we call that unrolling a loop, and that would get rid of the loop complexity. So then we're stuck with this. This is an immediate load, that's 2 cycles. That's 1 cycle, 1. It's also 2, and that's 1. Okay, if we've unrolled the loop, we won't need to see any more, so that would save a register, so we could switch back to using registers for this data. So we'd just be toggling a value. So that would be the equivalent of that. That's 7 cycles our loop would need to be. And then for each byte, we would need a couple of cycles to store it with probably a STOS-SB instruction. So a byte would be 7 times 8 plus 2. So we've got 4 megahertz. So that's about 71k a second. That's pretty fast. We've only got 64k of RAM, so the biggest single program we could load off a storage device over SPI with the software bit banging would take us just under a second to load. That's pretty good. But is it fast enough? Okay, 71k a second. That's actually pretty good. If we were loading programs, that's the largest program we could ever fit in memory, is going to take less than a second. So I'd be kind of happy with that. But it would be quite limiting at that speed if we wanted to do any kind of content streaming or anything more interesting like that. So do we want to go faster? Now, bit banging SPI means that we are quite limited in the rate. And the protocol is quite simple. I mean, I would imagine the hardware to handle the full protocol would probably be somewhere in between the SNES controller circuit and the UART circuit. But if we kind of did a bit of a hybrid, we could probably do this with quite a limited number of chips. So something I'm interested to hear back from you guys is, would you like me to do a full implementation of SPI? Or maybe a challenge partial implementation of SPI to increase the rate with as few supplementary chips as possible? Because I think we could go quite a long way with that. And I'm kind of leaning in that direction. Go for a simple circuit which gives us a higher transfer rate. Anyway, I hope you found this video interesting. I found it pretty rewarding actually, because I'm hoping we can put the RTC chip into the final build. And date and time is a nice little addition to be able to have. Kind of anchors the programs we're running into the real world a bit more. As always, big thanks to all of my patrons and other supporters. I really do appreciate it. And I hope everyone found it interesting. I will see you again soon. Goodbye. Okay, so it's now the following morning. I'm just getting ready for work, but I wanted to fire this up and see if the clock was actually holding time. I have to say that looks pretty good. So the date has rolled over. I pretty much started that when my phone was saying it was 9 AM. I think what it would be good to do is write some slightly better code for setting the time that makes it easier to get it lined up exactly with another time source, but the battery's clearly allowing it to hold time. I really like the idea of having a clock source and a backup battery that will allow it to display the current time on startup, but we've also got a reliable hundredths of a second timer here, which will be handy to do things like timing length of execution if we write a few library functions. It's not terribly high precision, but it's obviously a lot better than trying to manually time things externally.